Hello everybody, today I'll talk about the power dissipation of an accelerated charge. So we have here a charge at the center of this diagram with radial field lines, which is accelerated during a short period in time, which is delta t, to a speed delta v. Now we start off with calculating the dissipated energy, because there will be a ripple in the electromagnetic field that moves with the speed of light outwards and carries away energy. And we compute how much energy that is. So first, let's write down Coulomb's law. Phi of r, the potential, equals 1 over 4 pi epsilon 0 q over r. R is the distance, q is the charge. That leads to an electric field which is given by the negative gradient, and we can insert it's q over 4 pi epsilon 0 radius divided by r cubed, so the field falls with r squared. Now, looking again at the picture, the important thing to note is purely geometrically, we have a parallel and a perpendicular field component that's indicated here where the arrows are. Parallel means parallel with respect to the radius vector, and perpendicular is also perpendicular to the radius vector. If you look at the diagram, you will find that the perpendicular component in terms of the radial component is delta vt sine theta, and the parallel component is just c delta t. C delta t is the little distance, the little thickness of this outgoing electromagnetic wave during the time the acceleration happens, and the delta v times t times sine theta is the distance indicated here. It is the shift of the electric field lines induced by the movement. That's in principle all we need. The rest is electrodynamics and special relativity. So let's carry it through. We insert first the electric field that we have calculated. So we find for the normal component q over 4 pi epsilon 0 r squared. I write here this delta v over delta t times r sine theta over c squared. That's just by means of inserting, and we also used t equals r over c. So we can write this further as q v dot, that's the acceleration, times sine theta over 4 pi epsilon 0 r c squared. Good. It is important here to note that the perpendicular component falls with 1 over r. That already tells us that energy will be dissipated. Why is it? We need two ingredients to see this. First, in the vacuum, it holds that the magnitude of the B field in SE units is 1 over C times the magnitude of the E field, and B and E are perpendicular. Second, the definition of the Poynting vector, which is the vector along which an electromagnetic wave carries energy, is 1 over mu 0 times E field x B field. And because E and B field are perpendicular and only the perpendicular component of the E field, perpendicular to the radius vector, falls with 1 over r, we know that the pointing vector will point into the radial direction, and we can now collect all the terms, and basically with a 1 over c we just need to square the E field that we're having here. So we take q squared v dot squared sine squared theta divided by 16 pi squared epsilon mu squared mu 0, and then we write c to the fourth. I get an extra c here from the equation for the magnitude of the B field divided by r squared. Another important identity in Maxwell theory is epsilon mu times epsilon naught times mu naught times c squared equal 1. So we can remove this, this, and this. And we obtain for the pointing vector epsilon r times q squared v dot squared times sine squared theta divided by 16 pi squared epsilon 0 c cubed r squared. So there are a few things to note here. One is the sine squared theta, which gives us the angular dependence. Let me try to insert a picture here, because this sine squared, here it is, this sine squared theta leads to a donut shaped, where you see a donut here, and the arrow points in the direction of the acceleration, not the movement, but the acceleration. So we have the donut shape radiation pattern. Let me remove it again. What we're doing next is we integrate the pointing vector over a surface area to compute the total dissipated energy. That's straightforward to do. We write for the dissipated power P of our accelerated charge, d omega times s in the radial unit vector. We just need to insert. I put all the factors in front, q v dot squared of the integral. This is a 16 pi squared c cubed epsilon 0 r squared. And then we have integral from 0 to 2 pi r d phi and integral 0 to pi r sine theta. I write it like this: sine squared theta, that's our sine squared theta, d theta. So again, we can cancel the r squared. We see that only the perpendicular component, which enters squared here, so it gives the 1 over r squared, cancels the r's in the line elements here. So this will contribute. It's clear, I think, nothing depends on phi. This integral will give 2 pi. And if you do an elementary calculation, you will find that this integral is 4 over 3. So we multiply all the factors, and we obtain q squared times v dot squared divided by 6 pi epsilon 0. Okay, this is a famous Lamar's equation. It is the total dissipated energy of a charge that is accelerated. Good. It is, however, non-relativistic. Now, we can make it relativistically, however, and that can be done by a fairly simple trick. Now, consider that the left-hand side is a power. A power is a Lorentz scalar. Why is it so? If you look at the energy transforms with relativistic gamma factor. The time also transforms with a relativistic gamma factor under Lorentz transformations. That means that their ratio P does not transform. It transforms as a scalar, so trivially. Hence, it is a Lorentz scalar. Now, because the left-hand side of this equation is a Lorentz scalar, the right-hand side must be a Lorentz scalar too. And because it is clearly not in this writing, when it's written like that, but it can now be made into a Lorentz scalar only by using the covariant form of the derivatives that appear on the right-hand side. So let's do it. We write P equal Q squared over 6 pi epsilon 0 m squared c cubed, and I write this as dp dt. That's the Lorentz. That's not Lorentz invariant. And I write this as, in its Lorentz invariant form, it's not equal, actually I can draw an arrow here, a minus sign that you'll understand in a second, q squared c divided by 6 pi epsilon 0 m, that's wrong, mc squared squared. That's the same number of factors of c. The p mu with respect to tau times the p lower index with respect to tau. So this is the bottom line is the covariant form of the top line, and the minus sign that's appearing here is explained by the minus that we pick up in the contraction of this Lorentz Lorentz indices in this Lorentz invariant in product. We can expand this back into components, and there's always the same prefactor, mc squared squared times, and here we have now dp with respect to the proper time, d tau minus 1 over c squared dE with respect to d tau squared. So tau here is the proper time. It's important that we know how to transform the differential, and this is just dt equals gamma d tau. So one picks up extra factors of gamma, and there's a 1 over c squared term in the formula that is also a relativistic correction. So write p here, and we have obtained now the Lorentz invariant form of the power dissipation of an accelerated charge. So now we can consider relativistic and ultra-relativistic particles and look at their energy dissipation according to their movement. We do two examples that are important for collider physics. One is linear acceleration. Linear acceleration. This is computed using a little trick. For linear acceleration, I write down the formula for the energy squared. I write mc squared squared plus p squared c squared. That's the energy momentum relation for our accelerated particle, and I differentiate this with respect to tau. I find 2 times e dE d tau equals c squared p in dp d tau. In other words, bring everything, there's a factor of 2 missing here, bring everything on the same side, we can compute the e d tau equals c squared p over e times dp d tau. So that's one important relation. And now we write the momentum and the energy in terms of the relativistic gamma factors. So the momentum is just, I have the c squared on top here, is just gamma mv, the velocity. This here is the momentum p, divided by the energy, which is just gamma m c squared. And then we have here dp with respect to d tau. And so we find that this is just v, the velocity, times dp with respect to d tau. So we now have a formula for the energy differentiated with respect to the proper time. And we insert this in our equation for the power dissipation into the Lorentz invariant form of Lamar's equation. Now, if we do that, we find P equals Q squared C over 6 pi epsilon 0 mc squared squared. We had there dp with respect to d tau, that's the first term, is unchanged. And it enters squared, so we get the v squared over c squared. And then we have the same factor. And this last parenthesis becomes 1 minus beta squared times dp with respect to d tau squared. But this 1 minus beta squared is just the 1 over gamma squared. And now we can compare we can combine the 1 over gamma squared with the square of the d tau in the differentiation, and this becomes dp with respect to d gamma tau squared, which is just dp with respect to dt squared, where t is the time in the lab system. Good. So we can express our power dissipation in principle in terms of quantities that are not measured in the frame of the particle, but in the lab frame. dp with respect to dp over dp differentiated with respect to dt, we can replace that by the energy gradient in linear acceleration, because the energy change over a distance the particle travels will amount to a change in the momentum. And typical gradients that we find are 25 MeV per meter. These are the typical gradients that are achievable in linear accelerators. So our calculation was useful because we can now use these lab frame quantities. Let's write Lamar's equation once more. Nothing really changed. The prefactors are the same. It's just that we found that the last term is can be replaced by the e dx squared. Now we can put in some numbers. We can take the electric charge as 1.6 times 10 to the minus 19 Coulomb. We can take the speed of light 3 times 10 to the 8 meter per second. We can take epsilon 0 as 8.854 times 10 to the minus 12 Coulomb per voltmeter. And we take the mass of the particle, which we take to be an electron, as 0.911 times 10 to the minus 30 kilogram. These are the numbers that we need. And if we plug everything together, we find P equals 1.1 times 10 to the minus 16 watt, which is a tiny number. That means Lamar's equation tells us that a charge that's linearly accelerated dissipates almost no energy. Hence, we can build linear colliders and need not worry about the charge dissipation. Now let's do one more thing. We can compute the energy efficiency. That is the energy efficiency of the electron in producing radiation. So we call this object eta, and it is just the power that's dissipated divided by the change in the energy of the electron. We can compute this by replacing the differential of the derivative in the denominator, which we can do in this way by replacing it by V times dE over dx, where the dE over dx is our 25 MeV per meter. And in terms of expression, this becomes q squared over 6 pi epsilon 0 times 1 over mc squared times 1 over beta dE dx. And if you insert the numbers here, you get an energy efficiency of very roughly 10 to the minus 13, which means it's extremely inefficient to produce electromagnetic radiation by linearly accelerating a charge. It's not efficient at all. Good. That's a different way of saying what we already knew. Now let's do a completely different example. It's a bit simpler in terms of mathematics, but physics is completely different. Circular motion. Circular motion of a relativistic particle. First, the circular motion does not change the energy, so we know dE with respect to dt is certainly 0. The other thing we know is that the momentum change in time, because it's circular motion, is just omega times p. This omega, that's could be the cyclotron frequency of a particle in an accelerator, for example. It's a velocity over r, and then we had a momentum p. Now we make the ultra-relativistic limit, which is easy to do here. This becomes c over r, c over r times c over r times p, and this is just the energy divided by the radius, because in the ultra-relativistic limit we can neglect the particle's rest mass. Okay, this is all we need to know. Now we insert again into the Larmor equation. So we had P equals Q squared times C divided by 6 pi epsilon 0, and now I take out a factor gamma squared divided by mc squared that we had before, and I did this in the proper time differential, which I replace with a time differential of the lab frame. So this gamma here on top is the gamma that comes from the tau in the differentiation. We just have computed dp with respect to dt, and therefore we only need to insert q squared c over 6 pi epsilon 0. I rewrite the gamma factor by e over mc squared divided by mc squared, and I insert what we've just computed. If you think for a moment, you will realize that the directions of the vectors, they work out, so that we can compute the vectorial dp with respect to dt squared with the scalar quantity we've computed above. And it remains to be written one more time. 1 over mc squared to the 4th times e to the 4th divided by r squared. And this formula is very important in the design of accelerators, because, well, it tells us many things. First of all, the power dissipation of a charge that's on a circular motion as a function of the mass is suppressed by the 4th power in the mass. So in particular, because we know the mass of the proton divided by the mass of the electron to the 4th power, that's very roughly 1836 to the 4th power, which is 1.1 times 10 to the 14. That's the suppression factor when you replace electrons with protons at the same energy. That means a proton collider almost has no synchrotron radiation. There's almost no radiation from highly energetic protons on a circular beam, because the suppression factor is 10 to the 14, and that just makes this for the energies that we have achievable is completely negligible. That's one thing. The other thing is Now, if we talk about electrons, the synchrotron radiation, which is the total power, which is the power that's radiated off by the electromagnetic interactions, it grows with the fourth power of the energy. So we can expect that synchrotron radiation for electrons is negligible until we literally hit a wall when we try to increase the energy. Moreover, we can reduce synchrotron radiation by making the accelerator large. But you have a fourth power in the energy, and you can beat that only with a squared in the radius. So you're really fighting a tough beast here. Increase the energy a little bit. You need to increase the radius by a lot more, and that is expensive, to achieve the same synchrotron radiation. Now, in the lecture, we learned that for Lab 2, the E plus E minus collider in the 27 kilometer tunnel, when it ran with 70 GeV, the loss per turn was 700 kiloelectron volts. This leads to a damping time of roughly 50 milliseconds. The energy was then increased from 70 GeV to 104 GeV, so 30%, and the energy loss per term increased fourfold, which led to an energy damping time of the beam energy to 18 milliseconds. So at this maximum energy, it was almost synchrotron radiation was absolutely limiting in keeping the beam alive. It would just radiate away its energy within milliseconds. Whereas much higher energies for the LHC of 7 tera electron volts, because they are protons, the synchrotron radiation is suppressed enormously, and the damping time of the beam is 1.5 days, which is in the vicinity of the duty cycle of the machine. So it's absolutely not important. Okay. One final thing. What is the shape of synchrotron radiation? Now, we said it is a donut. However, the donut now needs to be Lorentz transformed. Let's look at it. Is this picture here? I hope it shows up. Yep, here it is. The middle axis of the donut points towards the acceleration, which is inside the radius of the circular motion, and this donut is now Lorentz transformed in the direction of the movement, and the width of the donut is compressed by a factor of 1 over gamma, and we can quickly check this calculation. That's easily done by considering the Lorentz transformation of an angle. We can do this in the following way. Let's write down the Lorentz vector of the direction of a photon in this way, and we multiply this with the Lorentz transformation, gamma, beta gamma, beta gamma, gamma, yes. So that's That's the Lorentz transformation. That is the direction of the photon. And this becomes sine theta, doesn't change. Here we find beta gamma plus gamma cosine theta, and the other two components are not very important. I write them down anyway, just so that the calculation is complete. And here there should be a 0. And from this we can read off that the tangent of the transformed angle is just sine theta over gamma divided by cosine theta plus beta. So what you see here is, first of all, the transformation of the angle has the correct limit if beta goes to 0 and gamma goes to 1. And you also see that the gamma factor, if the gamma factor in the denominator is large, the tangent is reduced and the radiation is collimated very strongly in the movement of the direction. Good. I think we've learned a lot about synchrotron radiation, and I hope these little calculations support you when you study for the lecture. That's all. Thank you.